right, ladies and gentlemen, welcome to another round of information. This is AP Chemistry. This is Mr. Doolin. Thanks for tuning in. Today we're going to look at the dissolution process. Some people would refer to this as solubility, or what happens when something actually dissolves. And so really you just need to know the dissolution process. We're really just talking about substances dissolving. And the general idea behind dissolving is just we've got forces that hold molecules together. Right, that. And then those are either as intermolecular forces, and so I've got both intermolecular forces, or that's between molecules, and then I also have intra, which are my forces that we would normally refer to as a bond. So intermolecular forces between the molecules, intramolecular forces, those are my actual bonds. Most of these that we're going to look at today that are a bond are from ionic compounds. And remember, an ionic compound is actually just a cation and an anion that are attracted to each other because of that opposite charge, that Coulombic force, all right? And so the thing that we need to understand, if we have forces that hold molecules together and hold these atoms together, these forces have to be overcome in order for something to dissolve. So, and really, because what I'm saying is if I have two atoms together, right, and they're sitting there, I drop them into a bucket of water, the water has to have more force or more attraction to these molecules than the molecules do to each other. Otherwise, the molecules will just stick together and nothing will actually happen, all right? And so in the particular case, what happens is the water will come in and it will pull in one direction, and it'll take those molecules apart, all right? And then it'll coat them in a hydration shell, and we'll talk about that in just a second, all right? Another big idea that we want to make a distinction of right at the beginning is that our ionic compounds actually do something special and unique that covalent compounds don't generally do. So our ionic compounds and our acids, right, dissociate. And what that means is if we go back, and I'll show you an example right here, that our ionic compounds, again, they're positive, negative. So if I've got like an NaCl, which is just sodium chloride, if it were to dissociate, what happens is the water will actually pull the Na so that I end up with Na+, and then it will also pull the Cl so that I end up with Cl. And believe it or not, because when we talk about NaCl, this is an ionic bond, right? So it's an actual bond. It has the strength and the force of a bond, but the water is able to pull them apart. And so you would wonder, then yes, what I just said earlier, right? The forces have to be overcome between these bonds to have something dissolve. And we know salt will dissolve in water, right? And so really, really, really important concept to understand. Ionic compounds dissociate. Covalent compounds do not. Acids also will dissociate, all right? Our strong acids will dissociate completely. Our weak acids will not dissociate completely. So that's a blast back from the past, all right? And so what we want to do is I want to take a closer look at this NaCl, and I'm going to make the Na one color, and I'm going to make the Cl another, all right? And so what ends up happening is if I drop this sucker in water, now let's take a look at water really quick also. I've got a water molecule, I've got an oxygen, right? And then I also have two hydrogens. Now this molecule is polar. We remember water being polar. If I were to draw just the skeleton structure of it, I've got the oxygen with two hydrogens, I've got two lone pairs on the oxygen. We would call this molecule where we have a delta positive or a partial positive, a delta positive, and a delta negative. So water is a polar molecule. That deals with the electronegativity differences from, think back to your pre-AP days where oxygen has a much stronger attraction to all those electrons, so it pulls them towards one side of the molecule, so we end up with a partial negative side and a partial positive side to water, all right? And so pay attention to how I've got it, right? The blues represent the water, the reds represent the oxygen. And so let's take a look. When I drop salt into water, what actually happens? So I'll end up with, let me stay with my colors here. I'll end up with a sodium molecule, right? And then I'll also have my chlorine molecule, and let me make them to scale. This should actually be a little bit smaller, again, just because of atomic radius. And so this is my sodium is a positive ion, my chlorine is a negative ion. And so what happens with the water? Well, I'm going to go ahead and put 4 water molecules around the sodium. I got the oxygen there, and then you can understand when I put the hydrogens back away from that positive charge. And again, this is all Coulombic forces. This is all a positive-negative interaction. And so again, if we go back up to the oxygen, I'm looking back up here. Remember, that's the negative side of the oxygen, right? The hydrogens are the partial positive side of the molecules, and so it should make sense that the partial negative sides of these water molecules actually line up and coat that positive charge of the sodium. All right. Now to go to the opposite over here, again, I'm going to put 4 water molecules around this chlorine, but this time I'm actually going to draw the hydrogens on the opposite side. And again, it deals with these Coulombic interactions, these positive, these negative interactions between the ions and the water that drive the orientation of the water. And it's also these interactions that is stronger than the interaction between sodium and chlorine and actually gets these things to completely dissociate. All right? Okay, and so again, remember these are my partial positive side of the molecules. And just make sure that when you draw these ionic compounds, when they dissociate, the water orientation is very, 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 very important to how that's going to look. All right, you need to make sure that you get the orientation correct. Now, one thing we are going to take a look at as well is called lattice energy. And the definition of lattice energy is how much energy it takes to cause that dissociation, to break apart an ionic crystal. All right, because I've got all these positive ions, negative ions oriented inside that crystal. So how much energy actually has to be put in to overcome those interactions? And it's actually based on Coulomb's law, and I actually hope you wrote the definition down there. I didn't write it down. And so I'm going to abbreviate this as the lattice energy is a force, and it's equal, we've got the constant there, and I've got charge 1, charge 2 over r squared. And so the bigger the charges are, the more force I need to overcome, or the smaller my ions, the more force I need to overcome. And so let's take a look at an example of that. I'm going to write NaCl. So again, I got a +1, -1 in this particular case, versus, let's say, a calcium chloride, where I now have a +2, and then I've got a -1 and a -1. And so I have to ask the question, out of these two, if we were going to put them head to head, which one would have a higher lattice energy? Which one would be less soluble in water? Right? And it goes back to and I'll actually, you know what? I'm going to let you answer that question to see if you can apply Coulomb's law to what we're actually talking here. But remember, larger charges, more force to overcome. Right? And so we would expect that to affect the solubility. Now, let's take a look, because this has been all about ionic compounds. I want to make something perfectly clear. I haven't mentioned covalent compounds, and there's a big reason for that. Compounds, right? So covalent compounds do not dissociate. Do not dissociate. Covalent compounds do not dissociate. You get the picture there? Okay. And so, but they generally, only your polar covalent compounds are going to dissolve in water, right? And again, it's because of a polar compound is going to have those partial negatives, partial positives in them, and that water is going to be able to take that to a lower energy state and actually have that attraction, right, because of that positive-negative interaction. And so it's still, the solubility here for the covalent compounds and the polarity is still because of those Coulombic interactions, all right? Now, the covalent compounds we generally will not draw out just because they're more complex because of those three-dimensional shapes, and the molecules get a little bit more complicated, and they have polarity differences within the molecule, and so it's not always completely clear about how the water molecules orient themselves around or those particular ones. So if you're ever asked to draw the dissociation or dissolution process, 99% of the time that's going to be an ionic compound, because it's very clear those positive ions, negative ions dissociate, and then the water orients themselves around based on the polarity of water. All right, and then I'm going to go ahead and clear, and I'm going to write this last statement because this is completely important for you to understanding. For something to dissolve, we actually have to have a couple of things happen. The solute, which is what's dissolving, and the solvent, what it's dissolving in, interactions, has to be greater. So we're going to say, let me go ahead and write interactions. Has to be greater. Right? So more force involved in that than the solute interaction. And I put Dan there. There you go. So for something to dissolve, the solute solvent, so the interaction between what I'm dissolving and what I'm dissolving it in, that interaction has to be greater than the interaction between the solute molecules themselves. And if that's the case, then we can actually get something to dissolve. All right? Okay, so that's it. That wraps up dissociation and dissolution. If you have any questions, be sure you write them down. Hey, answer that sodium chloride, calcium chloride question. See if you can get that, right? Because that's going to show some understanding of what you just heard. Make sure you get your summary. If you have any questions, bring them to class. We'll talk about them, and I will see you there.